Welcome to an eye-opening exploration of the most critical elements you've likely never heard of. Today, we're diving deep into the world of rare earth elements, 17 obscure minerals that have silently become the backbone of our modern civilization. From the smartphone in your pocket to the national security apparatus protecting entire nations, these elements are the invisible force behind our technological revolution. Join us as we uncover how these little-known materials are reshaping geopolitics, challenging environmental sustainability, and driving innovation in ways that affect every aspect of our lives. Deep within the periodic table lies a group of 17 elements collectively known as rare earth elements or REEs. Despite their name, most aren't particularly rare in Earth's crust, but they rarely occur in concentrated, economically viable deposits. These elements include neodymium, dysprosium, terbium, and lanthanum, names that may sound alien to most people, yet they've become absolutely essential to our modern world. What makes these elements so special are their unique magnetic, luminescent, and electrochemical properties. These properties make them irreplaceable components in everything from wind turbines to electric vehicles, smartphones, and sophisticated military equipment. Currently, global production sits at approximately 280,000 metric tons annually, but experts project demand will surge to 400,000 tons by 2030, driven largely by the accelerating adoption of green technologies worldwide. What makes the rare earth situation particularly precarious is that one country, China, currently controls roughly 85% of the global processing capacity for these minerals. This creates what security analysts call a single point of failure in the supply chain for critical technologies. Unlike oil, where multiple major producers exist across the globe, the rare earth supply chain represents an unprecedented monopoly in modern resource economics. This concentration of power has led to extreme price volatility that can devastate manufacturing plans. In 2011, we saw a dramatic example of this when dysprosium oxide prices skyrocketed from $166 per kilogram to over $2,000 per kilogram in just a few months. This sudden price spike forced manufacturers worldwide to reconsider entire product lines and highlighted the vulnerability of global supply chains dependent on these crucial elements. The applications of rare earth elements are astonishingly diverse and touch virtually every aspect of modern technology. Neodymium creates the world's strongest permanent magnets, which are essential for electric vehicle motors and wind turbine generators. Without neodymium magnets, these technologies would be significantly less efficient and more expensive. Europium provides the red color on television and computer screens, creating the vibrant displays we've come to expect from our devices. Yttrium strengthens various alloys and is crucial in laser technology, including the lasers used in precision manufacturing and medical procedures. Cerium is used in catalytic converters to reduce vehicle emissions and for polishing precision optical surfaces like camera lenses and telescope mirrors. Without these elements, much of our modern technology would simply cease functioning or require dramatic redesigns with inferior alternatives. The miniaturization of electronics, the efficiency of green energy, and the capabilities of modern medical equipment all depend on these little-known elements. The extraction and processing of rare earth elements presents a profound environmental paradox that's rarely discussed in conversations about green technology. These materials are essential for technologies that reduce carbon emissions, yet their production causes significant damage to local ecosystems. A single ton of rare earth oxide production generates approximately 2,000 tons of toxic waste. The Mountain Pass mine in California, once America's premier rare earth facility, illustrates this challenge perfectly. It was shuttered in 2002, partly due to environmental concerns after a series of wastewater spills containing radioactive material. Though the mine has since reopened under new management and stricter environmental protocols, it demonstrates the fundamental contradiction. The very materials needed to combat climate change require mining processes that can cause significant ecological harm. Studies in China's rare earth mining regions, particularly Inner Mongolia, have documented elevated cancer rates, respiratory issues, and soil contamination extending kilometers beyond mining sites. Acid mine drainage has contaminated groundwater in several provinces, creating what Chinese environmental researchers have termed cancer villages near processing facilities. The processing itself involves separating chemically similar elements, requiring large amounts of toxic acids and generating radioactive waste products. The Bayan Obo mining district in Inner Mongolia, which supplies approximately half of the world's rare earths, has created a tailings lake containing thorium and uranium that spans over 10 square kilometers. In surrounding areas, local groundwater has been rendered unusable for agriculture or human consumption. This environmental contradiction creates difficult ethical questions for climate policy advocates and consumers alike. How do we balance the immediate ecological damage of rare earth production against the long-term environmental benefits of renewable energy technologies that depend on these materials? Is it ethical to promote electric vehicles and solar panels if their production causes significant local environmental damage and health problems in mining communities? Some ecological economists have begun advocating for a more holistic life cycle emissions approach to green technology that accounts for the environmental costs of production from mining through manufacturing to disposal. This approach forces us to confront uncomfortable truths about the true cost of our technological progress. The communities bearing the environmental burden of rare earth mining are often far removed from those benefiting from the resulting technologies, creating questions of environmental justice and equitable distribution of environmental costs and benefits. As consumers become more aware of these hidden costs, pressure is mounting on companies to ensure ethical sourcing of these materials, similar to what occurred with conflict minerals like cobalt and tantalum in recent years. Rare earth elements have transformed from obscure entries on the periodic table to pawns in a global strategic competition. The control of these resources has become a matter of national security and economic sovereignty for countries around the world. In 2010, China briefly halted rare earth exports to Japan during a territorial dispute, sending shockwaves through international markets and prompting countries to reconsider their supply chain vulnerabilities. This single event catalyzed a global reassessment of rare earth dependencies. The United States has declared rare earths critical minerals essential for economic and national security, allocating over $700 million in recent legislation to develop domestic supply chains. The European Union launched its European Raw Materials Alliance specifically to address its 98% dependence on Chinese rare earth imports. Australia has strategically positioned itself as an alternative supplier, with companies like Lynas Rare Earths receiving government support to expand operations. Meanwhile, emerging reports indicate that Afghanistan may possess rare earth deposits worth up to $1 trillion, potentially transforming the region's geopolitical significance and adding another complex dimension to its troubled history. Various countries are now engaged in what analysts call mineral diplomacy, forming strategic partnerships with nations possessing these resources, often involving infrastructure development, technology transfer, and security arrangements in exchange for preferential access to rare earth supplies. The defense implications of rare earth elements are particularly significant and often overlooked in public discussions. Each F-35 fighter jet requires approximately 417 kilograms of rare earth materials for various components. Missile guidance systems, radar arrays, and night vision technology all depend on specific rare earth elements. Without secure access to these materials, advanced military capabilities could be compromised. This military dimension has elevated rare earths from economic concerns to national security priorities, with the Pentagon directly investing in domestic rare earth processing capabilities for the first time since the Cold War. Military planners now consider rare earth supply chains as strategic vulnerabilities that could be exploited during international conflicts. Defense contractors are working to develop stockpiles and alternative technologies, but the dependency remains significant. The militarization of rare earth policy represents a fundamental shift in how these resources are viewed, no longer simply industrial inputs but critical components of national security infrastructure. This has accelerated government involvement in what would otherwise be commercial mining and processing operations, with national security concerns sometimes overriding economic or environmental considerations. The vulnerability in rare earth supply chains has sparked a wave of innovation to reduce dependency on these critical materials. Researchers at Oak Ridge National Laboratory recently developed a new extraction process that can recover rare earth elements from electronic waste with 90% efficiency, a significant improvement over previous methods that could revolutionize how we source these materials. Toyota and other automakers have designed motors for electric vehicles that reduce or eliminate the need for dysprosium and terbium, two of the scarcest rare earths. These innovations demonstrate how supply chain concerns can drive technological advancement. Wind turbine manufacturers are exploring high-temperature superconductors that could eventually replace generator rare earth magnets, potentially eliminating a major source of rare earth demand. Perhaps most promising is the deep-sea mining potential, with recent surveys suggesting that polymetallic nodules on the Pacific Ocean floor contain concentrations of rare earths many times higher than terrestrial mines. The International Seabed Authority is developing regulations for this nascent industry, though environmental concerns remain significant about disrupting deep ocean ecosystems that are still poorly understood. Scientists are also working on developing synthetic alternatives that mimic the properties of rare earth elements. While these haven't yet matched the performance of natural rare earths, the research continues to advance, potentially offering a long-term solution to supply constraints. Recycling technologies are advancing rapidly and offer one of the most promising solutions to rare earth dependency. New chemical processes can extract rare earths from discarded electronics more efficiently than mining virgin ore, creating a circular economy for these precious materials. The European Union's Urban Mining Initiative aims to recover rare earths from the estimated 16 million tons of electronic waste generated annually worldwide. This approach recognizes that landfills and storage facilities containing discarded electronics represent some of the richest ore deposits of rare earths on the planet. Some analysts predict that by 2035, recycled materials could supply up to 25% of global rare earth demand, significantly reducing environmental impacts and supply vulnerabilities. Companies are developing automated systems that can disassemble electronic devices and sort components by material composition, dramatically improving the economics of electronics recycling. Consumer electronics companies are also beginning to design products with eventual recycling in mind, making disassembly easier and improving the recovery rates of valuable materials. The concept of materials passports is gaining traction, where products contain detailed information about their material composition to facilitate future recycling. This recycling revolution represents a fundamental shift in how we view resources, not as materials to be extracted, used, and discarded, but as assets to be managed and recirculated through the economy. As nations race to secure supplies of these critical minerals, the rare earth element supply chain has evolved from an obscure technical concern to a central feature of international relations and the green technology revolution. We're witnessing the emergence of new alliances and partnerships specifically formed around access to these materials. Countries with rare earth deposits are gaining newfound geopolitical leverage, while technology-dependent nations are developing sophisticated resource security strategies. Looking forward, we're likely to see continued tension between environmental protection, geopolitical competition, and technological innovation in this space. New mining projects are being developed in the United States, Australia, Canada, and several African nations, potentially diversifying the supply chain and reducing China's dominance. However, these projects face significant regulatory hurdles, environmental opposition, and economic challenges in competing with established Chinese operations. The race to control rare earth supply chains will likely intensify as green technology adoption accelerates and military applications continue to expand. Nations that successfully secure reliable access to these materials, whether through domestic production, international partnerships, recycling, or technological alternatives, will have a significant advantage in both economic development and national security in the coming decades. The rare earth challenge represents a perfect case study in how resource dependencies shape international relations in the 21st century. While rare earth politics plays out on the global stage, the impacts eventually reach consumers in ways few recognize. The availability and price of these elements directly affect the cost and capabilities of countless products we use daily. Smartphones, laptops, electric vehicles, and renewable energy systems all depend on stable supplies of these materials. When supply chains are disrupted or prices spike, manufacturers face difficult choices: absorb the increased costs, pass them on to consumers, or redesign products to use alternative materials with potentially inferior performance. Consumers rarely understand why their favorite devices suddenly become more expensive or why certain features might disappear in newer models. Understanding these hidden elements and their outsized importance provides crucial context for making informed purchasing decisions and participating in debates about technology, environmental policy, and international trade. As consumers become more aware of these dependencies, we may see growing demand for transparency about material sourcing and environmental impacts, similar to what has occurred with organic food labeling or fair trade certification. Companies that can demonstrate responsible sourcing of rare earths may gain competitive advantages as consumer awareness grows. The rare earth story ultimately connects individual consumer choices to global geopolitics in ways that remain invisible to most people. The story of rare earth elements represents one of the most consequential yet least understood aspects of our modern world. These 17 obscure elements have silently become the foundation upon which our technological society rests, from the clean energy revolution to national defense systems and the devices we carry in our pockets. As we've explored, their concentrated production creates unprecedented vulnerabilities, while their extraction presents a profound environmental paradox: materials essential for green technology causing significant ecological damage. The geopolitical competition for these resources is reshaping international relations, while spurring innovation in recycling, alternatives, and more sustainable extraction methods. As we move deeper into the 21st century, the nations and companies that successfully navigate the rare earth challenge will likely define the next era of technological development. For citizens and consumers, understanding these hidden elements provides crucial context for the complex trade-offs between environmental protection, technological progress, and national security that will shape our collective future. The rare earth story reminds us that even in our digital age, physical materials, and who controls them, still fundamentally determine the possibilities and limitations of human progress. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.